Alright, welcome back. This is 7.1 about the logarithm defined as an integral. This is section 7.1, problem number 12. Yeah. And it's another initial value problem. I figured I'd make a few of these videos because, it takes a couple of attempts to really get the process down. And, of course, there's always something that you have to do different with every different problem. So, in this case, we have dy dx equals 6 plus 1 over x. And so we're going to separate and get all the y values with the dy and all the x values with the dx. So we'll get dx over on the other side by multiplying both sides by dx. And what we'll end up with is dy equals 6 plus 1 over x dx. Now at this point we can take the integral of both sides. The integral of 1 dy is y. The integral of 6 plus 1 over x can be split due to linearity. So because differentiation is a linear function, we can, in fact, split this integral into two, taking 6 by itself and 1 over x by itself. And so the integral of 6 with respect to x is 6x. You might remember the derivative of ln of x is 1 over x. So likewise, the antiderivative of 1 over x is ln of x, and then we have to add a constant. But really quick, I'd like to explain. So if you remember, like I was just stating, the derivative with respect to x of ln of x is equal to 1 over x. And that's all fine and dandy, but when we go backwards, we notice there's a problem with the log function, which is that if you were to graph the natural log function, it would look something like this, if this was ln of x. And you would notice that we have major problems if x is a negative value, because the natural log isn't defined for when x is a negative value. And so for that reason, as a matter of fact, it's not even defined at 0. It's gone down to negative infinity at 0, at x equals 0, that is. And so because of that, we have to be careful when we are taking this backwards, because when we're taking the derivative of ln of x, we're fully aware of what ln of x looks like. It has no negative x values unless there's a horizontal shifter inside of the log. So when we're taking the derivative, we don't need to worry about where log doesn't have definable values. But when we're taking the integral, we do, because we don't know if x is going to be positive or negative. And for that reason, whenever we take the antiderivative of log, we write it as the absolute value inside of the log. So instead of ln of x, this is ln of the absolute value of x. And this is the reason why, more or less. So the next step of the initial value problem, now that we've solved this is called the general form of the differential equation, is now we're going to look for the particular solution, which is going to include this vertical shifter that will tell us where our function is pinned to the graph at. And so in order to do that, we'll notice here that y is a function of x, and so if we plug in 1 into y and get out 7, what that means is that when x is 1, y is 7. Because y of x equals y, right? Y of 1 equals 7. Therefore, when we plug in 1 for x, we get 7 out for y. And so we can now plug these in. If y is 7, then x is 1, so 6 times 1, plus the natural log of the absolute value of 1 plus c. Well, the natural log of the absolute value of 1 is 0. And of course, 6 times 1 is 6. So what we have is 7 equals 6 plus c. We can subtract 6 from both sides, and what we'll end up with is c plus 1. And this is the end of the initial value problem. We've now solved for what the constant is that tells us the particular solution, and we can come back and plug it in for c. And now we have the particular solution for this particular separable differential equation. So I hope this was helpful, and I'll see you next video.